Thank you. Thank you very much. So yeah, we're ready to start the last day of our conference. Okay, Oleg, I believe that you can start.
Okay. Good day. This work is joined with Alexander Pechin. Here we consider some quantum two-level open quantum system with coherent and incoherent controls. The talk shortly describes some part of our results for this quantum system, which were obtained in different directions. First, analytical and numerical results for time minimal control. Second, analytical descriptions of the system's reachability sets. Third, machine learning approach for suboptimal control. And you can see my abstract on the conference website also, of course. And let me start with some introduction. Quantum systems we can model behavior and control for different physical objects such as individual molecules, atoms, and so on. Quantum system can be closed, in other words, without interactions with the environments, accepting external controls provided by us. And another type of quantum systems is represented by open quantum systems, which has some interactions with the environment. And as mathematical tools for modeling, we can use different quantum mechanical equations, such as Schrödinger, Liouville, von Neumann for closed systems, Lindblad equation for open systems, for Markovian dynamics, and so on. After that, for quantum control, some words. We can have two parts of controls. Coherent controls for describing characteristics of lasers, and incoherent controls. Two parts of incoherent control actions can be used here. Incoherent radiation and some measurements, quantum measurements. And we have different aims for control. For example, breaking chemical bond in complex molecule. And for mathematical formulating such aims and tools, we can use the advantages of mathematical theory of control, of optimal control. We consider some control functions, control parameters, some cost criteria and constraints on control on states. We can have different constraints on magnitude, on spectrum, and so on. For obtaining optimal controls, we can use different optimization methods. For example, we can use gradient methods based on first order optimality conditions, for example, Pendragon maximum principle, and so on. Machine learning also can be used, and some particular results will be shown by me further today. And quantum control is important for developing quantum technologies. Further, let me show some short list of books and reviews on quantum control. First of all, I want to say about the book published in 1984 on quantum control, firstly in Russian, 1984, and after that, this book was translated to English and published in 1990. And this book by Budkovsky and Samoilenko further consider, for example, a good book written by David Tanner, as a book Alessandro, further consider reviews and for example, last year we have published this review in Russian Mathematical Surveys. It's translation of Успехи математических наук, and our review is devoted to some iterative methods for solving optimal control problems for quantum systems, and some introduction also was given here for quantum system, for quantum control. The next slide is for articles which consider both coherent and incoherent controls. The first two articles was published without me, and they are some basis for further last three articles. And in this paper, we considered that quantum system which is considered today. And the last two articles are used in the current presentation. And the first paper is devoted to more analytical things, and the last paper is about our approach for using machine learning, neural networks, and so on for suboptimal control. And let me consider the master equation. Gorinic, let me consider firstly this object, density matrix. In our case, we consider only two energy level systems. That's why this matrix is 2 by 2 matrix, and this Hermitian matrix with these properties. It's a definition for density matrix in our case. And after that, let me consider Gorinic-Kosakovsky-Sudarjan-Lindblad equation. This equation with some initial density matrix. This operator is Hamiltonian, and this part is free Hamiltonian, and after that we have some perturbation. V is coherent control, and H1 is some operator for describing interaction between the system and control actions. And after that, consider this part, this super operator. Super operator means that it is used for operators. And that's why we speak with term super. And this parameter gamma is larger than 1, and we model dissipative process with help of this super operator in this equation. Let me consider control n it is incoherent control. With help of this control, we can model influences to quantum system, and these influences are incoherent, in contrast to control V in our Hamiltonian. And these control are bounded with this condition. Let me consider different types of control classes for today's talk. Here we see piecewise continuous controls, and for machine learning we will use further piecewise constant controls. Next slide. Because today talk is about different directions, this slide is about reachable sets. In our case, reachable set for some fixed time final moment, T large, is the whole set of density matrices obtained, which is obtained by solving our master equation for all controls from our class. And time minimal control problem, which is written here, it is a problem where we want to satisfy this condition, terminal condition. In other words, it's needed to generate such final density matrix which coincides with some given target matrix, and it's needed to minimize the final time in the set of such pairs, the pairs which allow to satisfy this terminal condition. And of course, we see that the term of density matrix, the meaning, is connected with this time minimum control problem, because we consider such reachable sets which allow to satisfy our terminal condition. And after using the Bloch parametrization for density matrix, because we consider only two energy level system, we have good possibility to use classical Bloch parametrization. And this parametrization gives us rejection between matrix and corresponding Bloch vector. And for this vector, we have differential equation, which describes the evolution of this vector. And we will consider this formulation, because this formulation is easy to analyze, of course, and we have this good possibility. It's very good. And we rewrite the definition of reachable sets and the statement of our time minimum control problem. After that, let me consider some interesting class of time minimum control problems for using machine learning approach. Let me consider initial states, I mean for Bloch vectors here, which are located only on the Bloch sphere. And it's needed to mention that all Bloch vectors are situated in the Bloch ball. It's union ball in the three-dimensional real space. And let me consider initial states on the Bloch sphere. After distributing 200 points on the sphere, we have this picture. Two types of markers allow to show points which are situated in front and the back part of the sphere, and this B figure shows us some subset, only 50 points here. Further, let me consider piecewise constant controls for this consideration. And constraints on variations of these controls. We calculate jumps, absolute values, and take maximum values for both controls and restrict these values. Of course, we consider piecewise constant controls because, as you understand already, we want to consider parts of these controls as such parameters which should be considered as answers for machine learning. And as input information, we consider the coordinates of the points, Bloch vectors, represented initial density matrices. And after that, we can describe our machine learning approach as the following. First, we solve some series of trinomial control problems numerically using some optimization techniques. And we store this information as a training data set. After that, we consider the corresponding regression problem for obtaining such narrow network and other things for predicting controls and final time, of course, because it's time minimum control problem, which with appropriate accuracy allow us to consider these controls for our quantum system. I mean suboptimal solution here. And for testing, it's interesting to say about testing. I will say further. And for optimization problem, which is formulated here, we will use zeroth order optimization methods. And this composite objective function is used for taking into account both two criteria. I mean, it's needed to satisfy terminal condition, and it's needed to minimize the final time here. Of course, for this terminal constraint, we can use some threshold here, and some thresholds for constraints on the controls variations is also are considered here, and some additional constraints. These constraints allow us to restrict the space of answers. It's also important for machine learning, because if we have more than one solution for the same optimal control problem, and this optimal control problem is for some initial state, and after that, if we have some perturbation of this initial state and solve another optimal control problem for this some perturbated initial state, that we can have the situation where due to the possibility to have more than one solution for the same control problem, we can have the situation where answers, our optimized controls, can differ very large, and it's needed to restrict the class of controls, and that's why we have these constraints. Moreover, it's needed to restrict variations according to physical meaning, of course. And let me say some words about optimization methods. We use here only zeroth order optimization, and our objective function is written with using maximum and L1 norm here, and we use dual annealing and differential evolution methods here. Their implementations are available in the SciPy library. Some example, we consider 200 initial states and 200 optimal control problems here. Here we see the solution obtained for one of these time minimal control problems. We see that there are no large jumps for each time node here for both controls, and the obtaining trajectory inside the Bloch ball from the point located on the Bloch sphere to the target point here. And let me speak about the regression problem for finding suboptimal final times and controls based on the training data set. It's needed to formulate our regression problem, and it's important to write conditions about suboptimality. First, it's needed to restrict this distance. We allow some violation between the target point and the calculated final state of the system. But this error shouldn't be large. If this distance is large, then we have not good result from our machine learning methods. It's needed to try to find another architecture of neural network and so on. Of course, we consider statistically here. We consider different statistical characteristics. And it's needed to consider the predicted T time moment, which we want to find as with the following property. At least not much more than the arithmetical mean of the optimized final times known for the neighbor points located on the Bloch sphere. And if we find such a T which is significantly larger than the time moments for neighbor initial states, that it's some signal for us that we should change something in our architecture. And we use two methods. First, k-nearest neighbors, Of course, because we have neighbors, neighbor initial states for any point on the sphere, new point, which is not in the training data set. And after that, we consider some neural network. This tool from Skykin library was used, multi-layer neural network. And it's logical to combine these two ways. After that, consider this slide about some important remarks. First, of course, our main goal is to train such neural network which allow to predict controls for new points beyond our training data set. That's why it's not sufficient, of course, to consider only R² square for our training, and it's needed to analyze the results by integrating our control system and analyzing the obtaining final states here. And that's why we consider some large set of initial points distributed near uniformly on the sphere without coincidence with our points used for training. And statistically, we can use the corresponding results for analyzing the quality of our combining and particular algorithms for predicting. And it's needed to change some algorithmic parameters. For example, regularization parameter for avoiding overfitting, amounts of hidden neurons or hidden layers, and so on, for obtaining better characteristics of our results, considering statistical values. And the article prepared for the journal contains a good amount of plots, CDFs, and so on. Here only this plot. We considered 18 cases of the size of our training data set. As I said before, we consider 200 points on the sphere. It's the whole set of initial states, and the corresponding answers, optimized controls, and final optimized times are used for this point. Here we have the best result. This arithmetical mean of errors statistically over the whole testing set. And we see that if we decrease the number of the points or samples in our training data set, that the quality of our combined algorithm also decreases. The combined algorithm contain the method of neighbors, nearest neighbors, and neural networks approach. And in general, we see that the worst case here is with this value. It's not too large, not 1/2, not 1, because we have unit sphere. And after that, let me say some words about analytical results. It's interesting to consider the case when the system is controlled only with incoherent control. And let me consider these exact formulas for describing reachable sets when we have two cases of our initial state. This case, when we have the North Pole and we consider these values of our third coordinate, which can be obtained when we change the final time. We mix quantum states. Firstly, we is here pure quantum state, and after that we mix quantum states. And this case is opposite because the origin represents the completely mixed quantum state, and when we change the final time, we approximately solve the problem of purification of quantum states. And we see that we asymptotically achieve the North Pole here. And after that, let me say about time minimal control. Also for this particular class of controls and this type of target point, we see the following analytical results for minimization of final time. Also, for the initial point located, situated, which is our origin. And we see that these results were obtained analytically. It's interesting to consider the following numerical comparison because we see that for these different cases and the same target point, 1/2 here, and the same decoherence rate and the same upper bound for incoherent control, we see significantly different minimal times for achieving our target point. In other words, when we initially are situated in the North Pole, we very fast achieve the target point, and it's significantly slow to achieve this point when we initially situated in the origin. In other words, purification is such a problem which requires more time than mixing quantum states. This simple illustration, of course, it's only some particular class, some particular initial and target points, Also, we consider more general classes, numerical methods for estimating reachable sets. Last year, I talked about numerical estimating of reachable sets, and the video record is on the MassNet website, and you can watch this video. And after that, I say some words for conclusions. First, for the case of two energy levels, it is convenient to consider Bloch vectors instead of density matrices, because we have this good tool, I mean Bloch parametrization. And machine learning approach was applied here, and we have not bad results of our combined algorithm here. Of course, it's needed to continue such considerations. There are articles by another authors in the world about trying to apply machine learning for controls, for modeling differential equations, and so on. It's interesting direction, of course. And our analytical results for reachability and minimal time control illustrate interesting physical properties about purification, about mixing quantum states. It's interesting that it's possible to describe analytically such solutions even for such particular class of control. And it's interesting to describe numerically, and you can watch my last year presentation on the MassNet website for numerical results. And this work was performed in Steklov Mathematical Institute of Russian Academy of Sciences, and it was done under the supporting of the Russian Science Foundation. Maybe you can, you have some questions for me.
Yeah, thank you very much, Oleg, for the very interesting talk. So actually, we don't have so much time for questions, but I believe maybe at least one question.
Okay.
Okay. At least there is one question from me. So you said that you have used the following machine learning approach. So this is KNN and neural, like simple neural networks.
Yes.
So
simple.
Did you consider? Yeah. So did you consider maybe a little bit more sophisticated techniques like reinforcement learning or something more advanced? Or I don't know what is suitable for this problem.
Okay. Mikhail, thank you very much for your interesting question. Yes, it is important. As I said, nearest neighbors approach was used because we have a neighbor initial state. It's very logical to use this method first. Second, multi-layer neural networks, this classical object, of course, and this was used. We have some not bad results. You say about more sophisticated neural networks, and of course, it's interesting to consider reinforcement learning here, and there are publications about such results, and reinforcement learning was used later. And can be used later by us also. And I cannot say now about different neural networks, for example, convolutional neural networks and so on, because it's needed to try to take such object, and if we will have good results, if we will understand how to implement here using quantum properties, specifics, then we will have possibility to answer to a question. But now I cannot say about the results, because we have only our results shortly shown here.
Sure.
Of course.
Yeah, thank you very much. Yeah, it is.
Thank you,
very
Michael.
Interesting. Yeah, thank you. Okay, I believe that we should move on, because there is already time for the next speaker. And the next speaker, as I understand, is Nurbolat Kenbaev, who is a master student at Moscow Institute of Physics and Technology, and he will present his recent results on a interesting scheme of the quantum measurements with the post-selection. Okay, Nurbolat, I give you the floor.
Good
so
afternoon,
now you can
everybody.
Share your screen.
Can you hear me?
Yeah, loud and clear.
And can you see the presentation?
Yes.
Okay, let me start. We, under the strict guidance of my supervisor, Dr. Dmitry Kronberg, have investigated the possibility of increasing the Holevo value. I have divided my presentation into 5 main parts, and I will start with quantum channel. Generally speaking, quantum channel is a linear, completely positive, trace-preserving map of a quantum states. And any measurement, in principle, can be described via the Krauss representation, where Krauss operators contain information both about the measurement and how we handle the result of the measurement. In this way, the measurement is a specific case. We will consider classical quantum channel, which have classical signals in the input and quantum states at the output of the channel. For a given distribution, a quantitative characteristic of how much information can be transmitted over such channel with the classical outcomes after a particular measurement is mutual information. And the upper limit of mutual information in all possible measurements is the Holevo value, introduced by Alexander Holevo in 1973. It gives an estimate of the information that can be obtained from quantum states during the measurement. And we will investigate the possibility of increasing this Holevo value after the measurement with post-selection. And by the measurement with post-selection, we mean that some of the outcomes of the measurement are discarded, and then we work with the resulting states. And the increase in the Holevo value after the such measurement with post-selection follows from the monotonicity property of the relative entropy. We will see this jump above the Holevo value on the example of 2 mixed qubits. And first of all, we will see protocol B82. Quantum cryptography is a field of research whose main goal is to create devices and protocols such that the transmission of the information can be made in a secure way, preventing an eavesdropper from deciphering the message sent from one party to another. And it turns out that the possibility to transmit messages strongly depends on physical properties of information, and that there is a difference between quantum and classical data. We consider a problem where two remote users, traditionally called Alice and Bob, want to establish a shared secret key, a string of random bits that are unknown to the eavesdropper. In classical physics, it is possible to clone classical bits. So eavesdropper can intercept signals and obtain all the information without even being detected by Alice and Bob. This is a scenario working in classical physics. But in quantum physics, we can use non-orthogonal quantum states, and no eavesdropper can tamper with this task without being detected by legitimate users, because it's impossible always reliably distinguish between quantum states. Moreover, it is impossible to clone non-orthogonal states in order to gather more complete statistics of the measurement results. In this way, this strategy is safe according to the laws of quantum mechanics. Let me move on directly to the protocol B82. At each step of the protocol, Alice sends to Bob one of the two non-orthogonal states, phi0 and phi1. And the scalar product, cosine alpha, is the main parameter of the protocol. Here is important to note that we are only interested in the measurement outcomes, and we are not interested which states will be after the measurement. So it is convenient to use POVM formalism, which is a set of Hermitian operators that are non-negative and satisfies the completeness condition. If the system is prepared in the state ρ, then the probability of the outcome I after the measurement is given by this formula. As I mentioned above, Bob can't always distinguish between non-orthogonal states, phi0 and phi1. But Bob can make a measurement which sometimes will give him correct answer and will never give him wrong answer. Bob makes such an ambiguous discrimination. The first two outcomes correspond to precise results. For example, the outcome 0 corresponds to the state phi0 because the probability of the outcome 0 when Alice sent to Bob state phi1 is 0. Similarly, state phi0 doesn't give the outcome 1. In this way, first two results correspond to the precise results. But sometimes Bob will receive inconclusive outcome, and it will give no useful information to Bob. However, this measurement will not give him wrong answer, but sometimes he will obtain no useful information. Unfortunately, we can completely rule out inconclusive outcome, but we can minimize the probability of inconclusive outcome. We can do this by increasing the parameter C. We can increase it until the operator corresponding to the inconclusive outcome remains non-negative. And when its minimum eigenvalue becomes 0, we obtain the optimal value. Let us calculate this parameter. First of all, we calculate minimum eigenvalue, and when it becomes 0, we obtain the optimal value of parameter C. Moreover, operator p-fail can be derived like this. And the probability of an inconclusive result is cosine alpha. In this way, the optimal unambiguous state discrimination looks as follows. Let me remind of basic definitions. As I said before, we work with a classical quantum channel, which has classical signals at the input and quantum states at the output. And when we measure these states with observable pi, the probability of the outcome y, provided that the signal x was sent, is given by this formula. Thus, for a given measurement, the alphabets x and y are connected by the classical channel. The mutual information for this channel is given by this formula. Mutual information characterizes the rate of information transmission over the classical channel. The Holevo value of ensemble eta x rho x is defined as follows. It's the upper bound for mutual information, where h of rho is the von Neumann entropy of the density operator rho. And for mutual information and chi value, the following equation holds. That means that the chi value is the upper bound of mutual information over all possible measurements. And classical capacity of the channel is equal to this. According to the quantum coding theorem, it characterizes the upper bound on the information transmission rates. Then I will tell you about the Holevo value of the initial states. I consider the case where Alice encodes logical bits 0 and 1 with two mixed states rho 0 and rho 1, and sends to Bob with probabilities eta 0 and eta 1 respectively. The maximum amount of classical information that can be transmitted over quantum channel is determined by the Holevo value. Any two mixed states in a two-dimensional Hilbert space can be expressed as a convex combination of two linearly independent pair states. And without loss of generality, states phi0 and phi1 in standard basis can be expressed as follows. And if the states phi0 and phi1 are not orthogonal, it corresponds to the fact that the states rho 0 and rho 1 don't commute. Density matrices of the states rho 0 and rho 1 in the standard basis have the form 23 and 2 and 3. And to calculate the chi value of our ensemble, we have to, first of all, calculate the von Neumann entropy of the states rho 0 and rho 1. In order to calculate the von Neumann entropy, we first calculate the eigenvalues. We obtain such formulas, where h sub 2 is the binary entropy. Next, we shall calculate the von Neumann entropy for the average state. The density matrix of the average state can be written as follows in the standard basis. And after calculating the eigenvalues of the average state, we can obtain its von Neumann entropy. Finally, we can calculate the Holevo value of the initial states. On the graph, you can see its value for different configuration of states. For the further explanation of the final result, it is convenient to use definition of the quantum relative entropy. And using this definition with the definition of von Neumann entropy, we can rewrite the expression for the Holevo value as follows. Then we will calculate the mutual information. Unlike the B82 protocol, in this measurement, we are interested in the measurement results. And we are preparing states after the measurement. So we will switch to the Krauss representation, which is described by the following Krauss operators. This is a measurement where first two outcomes correspond to precise results, and in the case of outcome 0, Bobs prepares state E0, and in the case of state 1, outcome 1, he prepares state E1. But he doesn't do anything in the third outcome. He discards those outcomes. inconclusive outcomes. After this measurement, the state rho I goes to the state rho ig with probability pig. Thus, the initial states pass into the following. As I said before, we discard the outcome corresponding to G equal to fail. And after the selection, we get following states, rho 0 prime and rho 1 prime, where renormalization is given by this formula. Notice that this is correspond to the case with orthogonal states, E0 and E1. So this means that we have a convex combination of orthogonal states with coefficients given by this formula. Let us calculate these coefficients. We obtain that the coefficients completely coincide with the initial ones. If we choose the parameters C0, C0 and C1 equal, the optimal value of these parameters are determined from the fact that we can minimize the probability of the inconclusive result, as we did before in the protocol B82. In this way, we got a convex combination with the same coefficients, but with orthogonal states. Also, we can calculate the new probabilities of the obtained states, taking into account the probability of post-selection. By Bayes' formula, we have the following expressions. And we can see here that the probabilities also coincide. And therefore, it is reasonable to consider information characteristics for a fixed distribution eta. Finally, we get states rho 0 prime and rho 1 prime, which are a convex combination of the orthogonal states with the same probabilities. And if we measure those states in the basis E0 and E1, we obtain the classical channel. It's a binary asymmetric channel. And let us calculate the mutual information for this channel. By the definition, we have this formula, but it's convenient to write the mutual information in terms of relative entropy, as we did for the Holevo value. After the calculations, we obtain this equation, where rho prime is the average state for our new ensemble. Finally, we get this result. And on the graph, you can see the value of information with post-selection for different configuration of states. Then we will compare chi value and mutual information. One of the most important results of the quantum information theory is the Ullmann theorem on the monotonicity of the relative entropy under the action of a linear, completely positive trace-preserving maps. So this inequality holds. And strict inequality is realized for the non-unitary map. The inverse map to our measurement with post-selection is not unitary because it maps orthogonal states to non-orthogonal. In this way, we have the following equation. And comparing the Holevo value of the initial states with mutual information and using this inequality, we have the following inequality. So it tells us that the mutual information with post-selection is strictly greater than the Holevo value of the initial states. Generally speaking, the Holevo value is the upper bound of mutual information over all possible measurements. But here we discard inconclusive outcomes, and that gives us jump over the Holevo value. It can be seen from the graph that with individual measurement, the value of mutual information is strictly greater than the value of the Holevo value of the initial states. That brings me to the end of my presentation. I will briefly summarize the main issues. We have investigated the possibility of increasing the Holevo value when measuring with post-selection. And we have demonstrating an example with two mixed qubits. An increase in the Holevo value follows from the monotonicity property of relative entropy. And here is important to mention that this strategy works when initial states do not commute, which corresponds to the fact that the state phi0 is orthogonal to the state phi1. Obtained results are very important for quantum cryptography, since the amount of information that an eavesdropper can receive from transmitted quantum states is limited by their Holevo value. At the same time, legitimate users have the opportunity to perform post-selection, and which puts them in a more advantageous position compared to the eavesdropper. Thank you for your attention. Now I'm ready to answer your questions.
Yeah, thank you very much, Nurbolat, for a great talk. So, any questions? Okay, Nurbolat, maybe I have one. So, for the experimental realization, so did you consider any physical protocols or maybe schemes of the post-selection, like with the photons or some polarization mode or any physical approach? So did you consider this?
No, I haven't done it yet, but it may be possible because I have described unambiguous state discrimination, and there are some optical schemes to perform it.
Okay. So I'm just curious how hard is it experimentally to do this post-selection? But you said that this should be pretty easy. Okay, that's great. Thank you. Okay, if you have no question, then actually we're on time. So the next speaker is Asel Sagingalieva, who is a master student at Moscow Institute of Physics and Technology. And also she also helped us to organize this conference, also with Alexei Kodukhov, who gave a talk yesterday. So Asel, I'll give you the floor. And today she will tell us about interesting results in quantum cryptography and mainly new algorithms.
Thank you. Do you hear me?
Yes.
Okay. So let's start. We under the strict guidance of my supervisor have researched error correction algorithms in quantum cryptography, and my supervisor, Dr. Dmitry Anatolievich Kronberg. And so let's start. The quantum cryptography provides a solution to the problem of key distribution using the laws of quantum mechanics, which provide secrecy. And information about the key is transmitted through non-orthogonal quantum states. Unlike classical physics, in quantum mechanics, there is a theorem about the impossibility of cloning quantum states. It also follows from the laws of quantum mechanics that an attempt to measure a quantum state changes the state. Therefore, any actions of the eavesdropper can be detected by interference introduced into the channel. And in quantum protocol, there are several stages of key distribution. First, sending and measuring photons. It's about Alice sends quantum states to Bob. It can perform any action with them. For example, measure the states, separate by a beam splitter, and so on, before Bob gets these states. At the end of this step, Alice and Bob get a raw key, which includes errors and is correlated with how much information it was able to obtain. And second stage is key post-processing. And key post-processing includes basis reconciliation, error estimation. It's about if is not only the one responsible for the errors in the quantum channel. Errors during quantum communication can also occur because of noise in detector or other factors. So Alice and Bob must estimate the error rate and decide whether if listening or not. Then error correction, and it's about if number of errors doesn't exceed the value, then at the stage of error correction, these errors are found and corrected. At the same time, Alice and Bob should disclose as little information as possible using an agreed correction algorithm. As a result of the error correction stage, Alice and Bob have the key without errors, and if receives information including during the error correction stage, and after error correction, if has more information about the key. Then verification and privacy amplification, and it's about since Alice and Bob cannot prevent information leakage, they have to enhance secrecy of the key at the cost of reducing the key length. And Alice and Bob get a shorter string that if knows nothing or very little about. And after all this stage, the final key length is much less than the initial key. And accordingly, the efficiency of the quantum key distribution protocol decreases. And if you want to provide a high level of security, then the reduction in key length will be significant. Therefore, improving the efficiency of the error correction plays an important role in quantum cryptography. And here we will consider with linear codes, error correction with linear codes. And when transmitting on a noisy channel, a sequences of binary symbol, inversion may occur due to exposure to noise. While we cannot completely prevent this process, we can correct the effects of noise through coding. In a binary symmetric channel, each bit is transmitted unchanged with the probability 1 minus p or inverted with the probability p. And channel capacity of a binary channel, symmetric channel, described by the following formula. And Shannon's theorem says that if the channel capacity is C, then reliable transmission over the channel is possible for rates close to the channel capacity, and it is impossible for rates higher than the channel capacity. And the code makes it possible to transfer k bits of information using strings of length n, and code rates described by the following formula. And Shannon provides the existence of a code rate close to the channel capacity, for which the error probability tends to 0 as the code length tends to infinity. But Shannon's theorem is not constructive in the sense that it doesn't provide clues for finding such codes and how to efficiently encode and decode them. Practically implemented encoding and decoding methods use linear codes and will be discussed about below. And linear code is a set of bit strings that form linear space. This space can be described in two ways: through the basis generating matrix and through the solution of a homogeneous system of linear equations. This is given by the check matrix. The first way consists in specifying a generated matrix and allows you to convert an information word into a code word. And the code described using the generated matrix allows information to be encoded. And there is also a second way to define a linear code to detect and correct errors in the code. This way of settings consists in setting a check matrix. Elements of each row of the check matrix are the coefficients of the linear equation. Then the code words are the set of solutions to a homogeneous system of linear equations, which forms the check matrix. The check matrix allows you, again, to detect and correct errors that occur in code words after they are transmitted over the channel. Application of linear codes in quantum cryptography. After the stage of sending, measuring quantum states, discarding inconclusive outcomes, Alice and Bob have lines of length n, xa and xb respectively, which can be different. Alice string will be considered correct. Then Bob string contains error compared to the Alice string, where E is error vector. Next, Alice and Bob calculate their syndrome using this formula, and Alice tells Bob her syndrome. Bob subtracts Alice syndromes from his syndrome and gets error syndrome. Bob's task is to find error vector knowing the Alice syndrome. After finding the error syndrome, Bob adds his string with the error vector and gets Alice string. Since only thing Alice sends to Bob is Alice syndrome, you can count the number of bits disclosed as a result of error correction. The number of disclosed bits is the length of the syndrome. So, one example of the simplest linear code is repetition code. Its main advantage is ease of implementation, and this code converts information bit into its copies. That is, a repetition code with a code word length of n consists of one information bit and n minus one check bits, which repeats the information bit. The generated matrix for repetition code consists of one column and looks like this. The check matrix for repetition code looks like this, and the sum modulo 2 of the last and any other bit in the code word is 0. And the vector of errors in the code word with repetition coincides with the error syndrome. But if there are more than half of ones in it, then the zeros and ones must be swapped. Therefore, on the receiving side, Bob, knowing the error syndrome, can determine exactly which message was sent. Next, one of the most famous examples of linear code is Hamming code. Since the code corrects one error, therefore all columns of the check matrix must be different and not 0. Consider an example of a Hamming code with a check matrix of size 3 times 7. The length of the code word for such a code is 7. The size of transmitted useful information is 4 bits. It's easy to see that the length of syndrome is 3, and the syndrome is the column of the matrix, of the check matrix, in which the error occurred. That is, if, for example, the error occurred in the 5th position, then the 5th column of the check matrix will be the syndrome. This means that in the error vector, 1 will be only in the place where the number of the column of the check matrix coincides with the error syndrome. For our example, it is vector 0, 0, 0, 0, 1, 0, 0. This property of Hamming codes make decoding very easy. So next, let's consider another type of linear codes, LDPC code, low density parity check code. The main advantage of this code is effective decoding algorithms and possibility error correction close to the Shannon bound, as opposite to repetition code and Hamming code. LDPC codes are block linear code and can be represented as a check matrix. One of the features of this matrix is its sparseness. The number of zeros in it is much greater than ones. The sparseness property allows us to store in memory not to entire check matrix, but a matrix in which element in a row is the number of columns in which one is located is the corresponding row of the check matrix. This allows us to save computer memory. But the main advantage of LDPC codes is that they make it possible to quickly find the error syndrome due to algorithms that use a small number of ones in each line. Often, check matrix in LDPC code is represented as a bipartite channel graph. N left nodes, there are 10 of them called message nodes, and right nodes called check nodes. And the graph representation is similar to the matrix representation. And LDPC decoding algorithm, the algorithm is a messaging algorithm and is iterative. At each round, messages are transmitted from message nodes to the check nodes. Message represents the probability of accepting a certain value, in our case 1, given the message received from check nodes in the previous round. First step, calculation of the prior probabilities that come from the error estimate in the bits of the code word. Second step, horizontal step, there is a traversal through all check nodes and in each node by message nodes. Then the message is calculated from the check node to the message node. And third step, a vertical step, based on the probabilities calculated in the previous step. The probabilities in each bit are updated using following formulas. And fourth step, if Q more than half this Q, then nth bit in the code word is 1, otherwise is 0. If the test result was successful, that we exit the loop and we found a suitable code word. If the test result is negative, then we start the next round from the second step. We set a condition on the number of rounds, for example 50. If the code word could not be found after 50 iteration, we display an error message. And next, LDPC code work effectively with error rates up to 11%. And in order to effectively perform error correction with a high tier probability, a combination of a repetition code and an LDPC code can be used. For a word of length Kn, it is necessary split the word into n blocks of length K, then apply the repetition code for each block, and the resulting bit for each block with a calculated probability is an element in each of the n position of the word that is input to the LDPC. And this combination allows you to fix a higher probability up to half. And experiment results. On the basis of many experiments, a study was made of the efficiency of codes for different value. The graph shows the dependence of the code rate on different error values. Different colors indicate different length of the repetition code block, and the envelope shows a close approximation to the theoretical value according to the Channel theorem. And for each error, there is a code or a combination of code and block length in repetition code that work best for that error. The graph shows the final envelope where the best code variant is selected for each error. And in this paper, the solution to the problem of finding and correction errors for key distribution in quantum cryptography was considered, and when implemented error correction methods using linear code such as repetition code, Hamming code, LDPC code, a combination of repetition code and LDPC showed the best efficiency at a high tier probability. And constructed on the basis of a large number of experiments, the dependence of the code rate on the error demonstrates the possibility of a maximum approximation to the theoretical value that Shannon's theorem tells us. Thank you for your attention. Now I'm ready to answer your questions.
Thank you very much, Asel.
Thank you.
Yeah, so it's time for questions. Yeah, Asel, can you go to the conclusion section of the presentation? Yeah, thank you. So you found that this scheme is efficient at a high error probability, which is probably the most common experimental situation, right?
Yes.
Okay. So, yeah, but I believe that all the people in this room are, yeah, related to this work somehow. Okay, then probably we'll move on. Thank you again, Asel, for a nice talk.
Thank you.
And the next speaker is, so a little bit early, but the next speaker is Dr. Kronberg. So, Dr. Kronberg, are you here?
Hello, can you hear me?
Yeah, okay. Okay, great. And the next speaker is, as I said, Dr. Kronberg from Sterkov Mathematical Institute and also Moscow Institute of Physics and Technology. And he will present also some results in quantum cryptography. So I give you the word.
Oh, yes, thank you for the introduction. Well, let me see the full screen of my presentation. A moment. Oh, can you see the full screen now?
Yes, we can.
Oh, yes. Oh, yes, thank you. I'm going to tell you about some generalization of discrimination of symmetric coherent states and how we can apply this for eavesdropping in quantum cryptography. It is one of the possible applications, but actually I like eavesdropping, so that is what I selected as an application for this transformation. First, I will tell you a little bit about quantum cryptography and remind you about B9C2 protocol. Then I will tell about unambiguous state discrimination and how it works in quantum cryptography, why it is effective for the eavesdropper. And then about using symmetric coherent state as a countermeasure against unambiguous state discrimination attack. Then I will tell you about generalized unambiguous state discrimination, which I propose. And then a couple of words about the application for the eavesdropping in quantum cryptography. Well, the main task for quantum cryptography is a key distribution between Alice and Bob, which are the distant users, and they do not make any assumptions about the eavesdropper, no technological or computational assumptions. In B9C2 protocol, Alice uses two non-orthogonal states, and they use the fact that no one can discriminate between the states without errors. In this protocol, Bob performs a measurement with three outcomes, which is an ambiguous measurement. This measurement whether gives full information about the bit sent by Alice, or it yields an inconclusive result, and that is why the state is lost in case of inconclusive result. The closer are the states, that means that the higher is their inner product. The higher is inconclusive result probability. They are really difficult to discriminate. Then Alice and Bob use public authentic channel to discard the positions with inconclusive results, and then they perform the typical things for quantum cryptography, which are error correction and privacy amplification. But the problem for B9C2 protocol is unambiguous state discrimination attack, which works for any lossy channel between Alice and Bob. Here, Eve can perform the same measurement as Bob, and she can block the signal in case of inconclusive result. Or she uses her information to prepare the same state and uses lossless channel to send it to Bob. When the channel between Alice and Bob is long enough, then you can perform this attack without being detected, without introducing any error, and without introducing extra losses to the channel. Alice and Bob can resist this attack by making the states less distinguishable, but it is not a very good idea for them because they also suffer from the drop of key generation rate. They will get a lot of inconclusive results as well. There are common countermeasures in practical quantum cryptography against this attack, which include decoy states, strong reference pulse, which must reach the receiver side, and they can also include distributed encoding, like in Coherent one-way protocol and differential phase shift (DTD) protocol. Other possible countermeasure against the unambiguous state discrimination attack is using symmetric coherent states. Coherent states are widely used in quantum cryptography. They are easy to be generated, and they can be generated with attenuated lasers. And we can use the phase shift coding to set the proper phase to send the proper signal to Bob. They are described by one complex parameter, which consists with intensity and phase, with two real parameters. Here are four possible choices for the symmetric coherent states configuration, which consists of several symmetric states. The important thing about symmetric coherent states is the bound for their discrimination probability. For the set of n symmetric coherent states, there is a famous result by Sheffield and Barnett. They upper bound the probability for their unambiguous discrimination. That is why Alice and Bob can use a large number of symmetric coherent states so that the probability of unambiguous discrimination by if is very low. And that is why they can be used in quantum key distribution. That is the technology which is used in some proposed protocols, including Y00 protocol, and protocol on geometrically uniform states, and sidebound channel protocol. Well, the motivation of this work is to find a generalized discrimination between symmetric coherent states and to propose the USD-like attack based on this discrimination. It can be applied at shorter distances. Then we propose a USD-like transformation, which works for every given success probability, but it is a little bit weaker. So it does not make the states fully orthogonal. It does not extract full information from the states, but it makes them more distinguishable. After this transformation, you can take a part of each signal to her quantum memory and send the rest of the signal to Bob, like in the beam splitting attack scenario. And after basis reconciliation, which is done by Alice and Bob, if measures her state to get the Holevo value of the states in her quantum memory. So first she makes the transformation, she knows whether it was successful or not, and then if it was successful, then she puts a part of each signal to her quantum memory and sends the rest of the signal to Bob with her lossless channel. First, let us consider the orthogonalizing operation for the set of linearly independent pure states. In the paper, which is mentioned here by Tasaki and others, it was a theorem which states that if we have the set of linearly independent pure states, then such vectors are mutually orthogonal. Here, G is a Gramian operator, which is a convex combination of the vectors of their density matrices. That means that we can make a transformation which consists of two Krauss operators. The first one corresponds to success, and actually it changes the states like in this lemma. And the other outcome is fail, which means that the operation failed. They did not, the states are not mapped on the set of orthogonal states. So this transformation whether makes the states orthogonal or it destroys them. Success probability can be found from the condition that the expression within the square root must be non-negative. So that is the boundary for the success probability for this operation. Now we can, using these Krauss operators, we can consider a generalized discrimination, which is a very simple generalization. In case of success, this USD operation works like we are mapping the original states to the orthogonal sets E, G, and these output states are perfectly distinguishable. But in case of, let us now consider a generalized operation where we map the states which are more distinguishable. This operation can be described as very similar transformation, but with additional parameter p instead of 1 in the previous operation. So when we substitute 1 with p, then we get a generalized operation, which for p equals 1, it is the same, it is USD. But for p equals 0, it corresponds for doing nothing to the operation which has a unit success probability, but which does not change the original state. For other values of p between 0 and 1, this operation works as a generalization of unambiguous state discrimination. It makes the states more distinguishable with higher success probability, but it does not make them orthogonal. So it is sort of weaker version of unambiguous state discrimination, which can work for for every desired success probability. We can find the parameter p, which actually yields this success probability. Now, a couple of words about quantum key distribution with symmetric coherent states. Alice and Bob use n number of coherent states, which are divided into n over 2 bases. There is a phase shift within each basis, theta. For the left picture, the theta equals pi, and for the right picture, theta is much less than pi. So there are n states which are divided into n over 2 bases. Here are the states within each basis, which difference is in the relative phase, theta, between them. In QKD with symmetric coherent states, for each position, Alice chooses the basis and the bit value, and she sends corresponding state to Bob. Bob chooses the basis and performs a B92-like measurement, a measurement which can unambiguously discriminate between the 2 states within each basis, within this basis, or yields inconclusive result. Then Alice and Bob get their row strings, row case, and they discard the positions with inconclusive results and find the positions where the bases match. After discarding the positions with wrong basis and inconclusive result, they have their row case and perform error correction and privacy amplification. Now, once more about our attack strategy, which uses this transformation. Here, if blocks the pulses where her operation fails, and she takes a part of each pulse to her quantum memory for the signals where this operation was successful. This operation has higher success probability than the USD, so it can work for any distance between Alice and Bob, unlike USD, which for a large number of coherent states works only at very large distances. After basis reconciliation and post-processing steps by Alice and Bob, Eve extracts information from her part of the states which are in her quantum memory, like in the beam splitting attack scenario. If at the moment of attack, Eve does not try to discriminate between all the states, which uses a lot of resources for Eve, it is a very expensive operation, and does not try to guess the basis. She will have this information afterwards. So, if information, if transformation takes the form every state by Alice, becomes a state in Eve's, Bob's space and additional space in Eve's quantum memory, which is correlated with this Alice's state. The condition for this attack is that Bob's success probability, Bob's probability of detection, must remain the same as expected in a lossy channel without Eve. So this probability depends on the distance between Alice and Bob. After basis reconciliation, we can calculate Eve's information, which is given by Holevo value of 2 pure states within each basis, which correspond to the given basis B. That is the expression for Holevo value of Eve's states. Now, Eve's task is to find the best parameters, P, which is a parameter for this transformation, and beta, which is the intensity of states which go to Bob. These 2 parameters should be optimized to maximize the information for the given channel L, the Eve's information. We also should take into account these restrictions, that Bob should have the desired success probability. Well, here is the performance of this attack, the results. The line shows information between Alice and Eve for our attack scenario. And so x-axis is for channel length in kilometers. And the y-axis is for Eve information. The number of states here is 16, and the number of bases is 8. Phase shift within each basis is small for the left picture. It is pi over 8, and theta is pi for the right picture. So in the right picture, the states are emitted by Alice are good distinguishable. For the left picture, they are not very good distinguishable. Original intensity is 0.2 photon per pulse. I took these parameters from a system proposed by ITMO University. It is a working system which is actually presented on market. The attenuation coefficient is 0.2 decibel per kilometer. Here, the dotted line corresponds to the Holevo value of the initial states, original states of Alice. Here we can see that already at short distance, this attack outperforms the beam splitting attack. Actually, you can extract more information by this attack than with beam splitting attack, where if information is bounded by Holevo value. Actually, Eve here knows more than Alice, more than Bob about the signals within each basis, but Bob actually knows more because of the post-selection. This is the conclusion of my talk, that we proposed a generalization for unambiguous state discrimination operation. This generalization increases the distinguishability for every desired success probability. Then we applied this transformation to the set of symmetric coherent states and proposed a new attack strategy for the QKD protocols based on symmetric coherent states. And the important result is that Holevo value of Eve is larger than the original value for the original states at relatively short distances. So that's all. Thank you for your attention.
Thank you very much. It was a nice talk. Okay, so if you have any questions, it's time to ask them.
Question.
Yeah, sure.
Thank you for your talk. As far as I'm concerned, is the probability of success bigger in the case of generalized operation than in USD?
Yes, that's right.
So there is some trade-off between parameter P and the probability of success.
Yeah, P is not the success probability as well. We can find the success probability from this condition. Yes.
I mean, so we can increase the parameter P, but it will lead to the minimizing the probability of success. Yes. So there is some trade-off.
The larger the P, the lower is the success probability. For P equals 1, it is the success probability for unambiguous state discrimination, which is bounded by Shepard's and Barnett result.
So right. We have to find some optimal values of P and P success.
Yes, you're right.
Okay.
There is optimization task, and we actually should take into account two parameters, P and beta. Beta is the intensity of states which go to Bob. Actually, there are two parameters which should be optimized.
Okay, thank you.
Thank you. Dr. Kronberg, you have a slide where is this scheme and it has some kind of quantum memory. Yeah, can you a little bit elaborate what is the quantum memory in this case? So what are the properties?
The properties, actually, eavesdropper has unbounded capabilities. So here I assume that Eve has a very good quantum memory, which works for a very long time. And she just waits for basis reconciliation to know the correct basis in which she should perform her measurement.
Okay, thank you. Okay. Okay, any other questions? Okay, otherwise, I want to thank Dr. Kronberg for a nice talk. Thank you again. And I believe that this was the last talk of the morning session on today. Yeah, so we will continue in 2 hours at 4 o'clock on European Eastern Summer Time. So thank you all again and see you in 2 hours.
Thank you.